This is a video summarising all of the content in the third organic chemistry topic in AQA A-level Chemistry. In it we cover naming halogenoalkanes, nucleophilic substitution and elimination reactions, and ozone depletion using CFCs. Halogenoalkanes, also known as haloalkanes or haloalkanes in some of the other examples, are molecules in which one or more of the hydrogen atoms in an alkane has been replaced by a halogen atom. The names for the halogenoalkanes are based on the names for the straight chain alkanes. So we start by using our prefixes that refer to the number of carbon atoms in the longest chain. So if there's only one carbon, then we would have methane, 2 would be ethane, 3 would be propane, 4 butane, 5 pentane, and 6 hexane. Depending on which halogen atom is put in, we then need a different prefix. So if there's a fluorine atom, this would be fluoromethane or fluoroethane and so on. If it's chlorine, it will be chloro. If it's bromine, it's bromo. And if it's iodine, then it's iodo. So by that logic, this molecule, which is methane with one chlorine atom substituted, will be chloromethane. If I take this molecule, then I can't just name it bromo because that bromine atom could be placed on any one of these carbons. So this is going to be 2-bromohexane. So I use the number to indicate which carbon it's on. This molecule here has 2 bromines, so therefore it becomes 2,3-dibromohexane. But what if the situation is more complicated? This molecule is commonly known as halothane, but of course that's not its IUPAC name. So looking at this molecule, I could start counting at either end. My priority numbers will be the same regardless of which end I start at. So I'm going to start on the left, which is going to be with my highest reactive halogen, which is fluorine. So I'm going to work out the numbers based on that, but then I'm going to list them in alphabetical order. So of course that means bromo comes before chloro, chloro comes before fluoro, and fluoro would come before iodo, although I don't need it here. So that means I'm going to have 2-bromo, 2-chloro, 1,1,1-trifluoroethane. Halogenoalkanes can be described as being primary, secondary or tertiary depending on where the halogen atom is found. So here's our carbon to halogen bond. And if that carbon is a terminal carbon, in other words, if it's at the end of a chain, then we're going to refer to this as a primary halogenoalkane. Now, a good way to think of this is look at the carbon that's bonded to the halogen and then look at how many other carbons is it bonded to. So that carbon there only has one other carbon bonded to it, so therefore this is a primary halogenoalkane. On the other hand, that carbon that is bonded to the halogen could be in the middle of a row. So here we've got a secondary halogenoalkane because that central carbon is bonded to 2 other carbon atoms. And then here we have a molecule where not only do we have that long carbon chain with the carbon bonded to the halogen in the centre of it, but actually that same carbon also has a methyl group coming off it. So that carbon is bonded to 3 different carbon atoms directly, and therefore this is a tertiary halogenoalkane. You'll have learnt as part of the bonding topic about the importance of electronegativity and how fluorine is an especially electronegative atom. So this means that if you have a fluoroalkane, you're going to have an incredibly polar bond. And this is also true to a lesser degree with the rest of the halogens. In a polar covalent bond, the electrons are unevenly shared, so they're more distributed towards the more electronegative atom, which in this instance is going to be the halogen. Hydrogen fluoride is a good example of this. So fluorine is really very electronegative, and so it draws the electrons in the bond between itself and hydrogen towards the fluorine, and that's going to cause it to become slightly negatively charged. Now, we're not talking about as much of a charge as if we had a negative ion and a positive ion, so we use the lowercase Greek letter delta to show a slight change. And so we're saying it's slightly negative and slightly positive. The exact same thing happens when a halogen is bonded to a carbon, although carbon is slightly more electronegative than hydrogen is, so the bond won't be quite as polar as that. Now, it is possible to have polar bonds within a molecule and the molecule not to be polar. And this can happen if the bonds are sort of in opposite directions to each other, if we have a symmetrical molecule, and in that case the slight partial charges will end up cancelling each other out. So in this example here, we've got tetrachloromethane, and because that molecule is symmetrical, even though all of the chlorines are ever so slightly negative, the positive bit of the molecule is actually inside in the middle. It's the carbon. And so it kind of almost doesn't matter that the outsides are slightly negative, because there isn't a positive bit of the molecule that can be attracted, so it's not going to cause us to have stronger weak intermolecular forces. So as I briefly alluded to, the reason we care about this polarity is because of the weak intermolecular forces. So there are three types of weak intermolecular force that you should know about from the bonding topic: van der Waals forces, which occur between all molecular substances; permanent dipole interactions, which occur between molecules that have polar bonds; and hydrogen bonding, which occurs between molecules that contain a hydrogen covalently bonded to either fluorine or oxygen or nitrogen. So in this instance, when we're thinking about our halogenoalkanes, we're expecting them to have permanent dipole interactions in addition to the weak van der Waals forces that they all have already. The only time that we would not see that permanent dipole interaction is if it's a symmetrical molecule, like the tetrachloromethane that we saw on the previous slide. These slightly stronger weak intermolecular forces mean that halogenoalkanes are going to have a higher melting and boiling point than the equivalent alkane, because it takes more energy to overcome these permanent dipole interactions than it does to overcome just van der Waals forces on their own. The high electronegativity of the halogen atoms, and therefore the consequential slight positive on the carbon, is also going to mean that halogenoalkanes are attractive to nucleophiles. So on to the new stuff. Halogenoalkanes undergo substitution reactions with nucleophiles, and there are three named examples here. Hydroxide and ammonia you're already quite familiar with, but the new one will be the cyanide ion. It's important to note that all three of these species have a lone pair of electrons, and also that both hydroxide and cyanide have got negative charges. But what actually is a nucleophile, and what is a nucleophilic substitution reaction? Well, literally, a nucleophile is something that is attracted to the nucleus, and this is going to be because it has a lone pair of electrons that it is able to donate. And when it does this, it's going to take the place of part of the molecule. Now, before we start looking at the mechanisms for these three substitutions, let's talk quickly about the polarity of those bonds in these halogenoalkanes. We've already said that the bond between the carbon and the halogen is extremely polar. Well, fluorine is the most electronegative element in the whole periodic table, and that means its bonds are incredibly polar, and that's going to make them stronger. So this means that fluoroalkanes don't react at all, whereas iodoalkanes react very rapidly. So before we start thinking about specific nucleophilic substitution reactions, let's just look at the general process. So we're always going to have a halogenoalkane. So there's a halogen group, which could be fluorine, although realistically we know that fluoroalkanes are very unlikely to react, so it's much more likely to be chlorine or bromine or iodine. You might also be given a molecule in which we refer to the R group, and that just means the rest of the molecule. You don't need to worry about it. You might have an R group, or you might actually have the rest of the alkane drawn out. Either way, it's not going to take part in this process. Now, because this is a nucleophilic substitution reaction, we have a nucleophile, and this can be represented as Nu. And you can see here it's really important that my nucleophile has got a lone pair, because otherwise it wouldn't be possible for this reaction to take place. And in a nucleophilic substitution reaction, the nucleophile is going to take the place of the halogen. So now the nucleophile is part of what was the halogenoalkane, and we've got this halide ion being kicked out, and we refer to this as the leaving group. There are a couple of other things that you should be aware of before we start drawing these mechanisms. The first one is that these arrows represent electrons. So here it's an electron pair, and therefore it's going to be a double-headed arrow. And that arrow is going to go from the electron pair to wherever it's going. So if I've got a hydroxide nucleophile like this, then my arrow should be going from that lone pair, which is on the oxygen. It should never be going from the hydrogen or from a different bit of the oxygen that wasn't the lone pair. Now, for our halogenoalkanes, in order to know where that nucleophile is going to attack, we need to know where there is a region of positive charge. So I'm going to put a delta positive on my carbon to show it's slightly positive, and a delta negative on my fluorine to show that it's slightly negative. So we've got this polar bond. And of course, electrons are negative, so my electrons are going to attack that slightly positive carbon there. Our first example of a nucleophilic substitution reaction is going to involve breaking a chemical bond using a hydroxide ion. So it's an example of a hydrolysis reaction. And here is the halogenoalkane that we're going to break apart. So pause the video and write down what it's called. If you said chloroethane, then you're right. Remember, when we've only got one substitute group and we've only got ethane, we're not going to have any numbers because whichever carbon I put it on, I would still just call it chloroethane. The first thing I'm going to do when I'm drawing this mechanism is that I'm going to make sure that my nucleophile has got a lone pair on it. And then I'm going to mark up my carbon-halogen bond to show that the carbon is slightly positive and the halogen is slightly negative. So then I'm going to draw my first arrow, and remember it's going to go from the lone pair of electrons to the slightly positive carbon. What's going to happen then is that this bond between the carbon and the halogen is going to break, and both of the electrons from that are going to be taken by the chlorine, which is our leaving group. So my second arrow goes from the middle of that bond to the chlorine to show that it's accepting both of the electrons. And then my products are going to be some ethanol, which is an alcohol, and then also this chloride ion. A more typical phrasing for an actual exam question would ask you to outline the mechanism for the nucleophilic substitution reaction of 1-iodopropane with sodium hydroxide. So the first thing I need to do is draw my 1-iodopropane, and like I keep doing, I'm going to add those delta positive, delta negative signs to the carbon-halogen bond. Then I'm going to add in my hydroxide ion, making sure that it's got a clear lone pair. My first arrow is going to go from that lone pair to the delta positive carbon, and my second arrow is going from the middle of that carbon-iodine bond just to the iodine. Then I can draw my products, which here are going to be propan-1-ol and that iodide leaving group. Now, hydroxide ions can and do act as a nucleophile and undergo substitution reactions, but also hydroxide ions can act as a base, in which case the reaction is a different type of reaction called an elimination reaction. Now, we're not going to worry about elimination reactions yet, but you do need to know which reaction conditions will promote substitution instead of elimination. So the first thing is that substitution is too slow at room temperature, and therefore the reaction needs to be warmed. The second thing is that being in aqueous solution promotes substitution. But halogenoalkanes won't dissolve in just water, so it also needs to be slightly ethanolic, and that ethanol is going to act as a solvent. We also need some hydroxide ions, so typically we use potassium or sodium hydroxide. Also, the type of halogenoalkane that we're using is also going to have an impact on whether we see substitution or elimination. So primary halogenoalkanes are more likely to undergo substitution reactions than secondary, which are more likely to undergo elimination reactions. Tertiary halogenoalkanes will do both. Now we're going to move on to substitution with a cyanide ion, this time with chloromethane. The mechanism for substitution with a cyanide ion is basically exactly the same as with a hydroxide ion, just we get different products. And the nice thing about doing substitution with a cyanide ion is it's a good way to add an additional carbon onto your carbon chain. So we're going to go through exactly the same process, starting with a lone pair on our nucleophile and drawing a curly arrow that goes to the delta positive carbon. Then from there, we're going to do a second arrow that goes from the middle of the carbon-halogen bond to the halogen. But of course, we're going to make different products compared to the hydroxide. So here, we're going to make ethane nitrile, which is a type of nitrile, and we'll worry more about them later in the course. But you might be thinking, well, how can it be ethane when we started with methane? But of course, we've just added in a carbon from our cyanide, so that's why it's F. You might also hear this molecule referred to as methyl cyanide, which is a valid name for it, but it's not the nomenclature system that AQA use. In order to undergo substitution with cyanide ions, again we want it warm, aqueous and alcoholic, but also we're going to have potassium cyanide instead of potassium hydroxide. There's one more type of substitution reaction to look at, this time using ammonia. This time we're going to use bromoethane as our starting molecule. Our final nucleophilic substitution mechanism is going to be with ammonia, and this is a little bit more complicated because whereas with the hydroxide and the cyanide ions, it was a single step process and we just had our starting species and our end species, this is going to be a multi-step process and we're going to need to draw some intermediates. The mechanism starts in exactly the same way. The lone pair on the nucleophile is going to attack the delta positive carbon, and then both of the electrons in the bond between that carbon and the halogen are going to be donated to the halogen atom. So we still get our bromide ion leaving group, but rather than being left with a neutral molecule, we're left with a cation. And if you think about it, this makes sense. We started with two neutral molecules, so at the end of this process, we still have to have overall neutral charge. So if we're losing an anion, we must be left with a cation. And you'll notice that this isn't a delta positive because we're not talking about just a tiny, tiny amount of charge. It is a full-blown charge. So that positive charge on one of the hydrogens bonded to that nitrogen is going to attract another lone pair from another nucleophile. So we actually need two molecules of ammonia for this process. So again, that lone pair is going to be attracted to something that is positively charged. And then what's going to happen is the nitrogen is going to withdraw the electron density from that bond. So we're going to have another arrow that goes from the middle of that nitrogen-hydrogen bond just up to the nitrogen. And so what we're left with is ethyl amine, which is obviously an amine, and also an ammonium ion. Nucleophilic substitution with ammonia is actually a reversible reaction, and that means that unless you have a really dramatic excess of ammonia, which is going to shift your equilibrium to the right-hand side, it's very hard to get a pure product. You just get lots of your reaction mixture still in there. So it's really important to have excess concentrated ammonia. It's also important that this is in ethanol rather than in water, because if you have water, then you'll just have some hydroxide ions in there and they will undergo the substitution instead. It's also important that this has to happen under very high pressure, and really the only way to do this is in a sealed tube. You can't heat the mixture under reflux because the ammonia would just escape up the condenser as a gas. In addition to undergoing substitution reactions, halogenoalkanes can also undergo an alternative reaction with hydroxide ions, and in this the hydroxide ions are acting as a base rather than as a nucleophile. This reaction is called elimination. So elimination means getting rid of something, and in this reaction we're going to get rid of a hydrogen halide, and the other product that's left behind is an alkene. So if hydroxide ions can act as a nucleophile and help substitution to happen, or as a base and help elimination to happen, then how can we decide which reaction will take place? Well, there are a couple of things that are different between them. Firstly, the temperature. Nucleophilic substitution is favoured by cooler temperatures, although you do often have to warm the reaction a little bit so that it doesn't go really, really slowly. But a hot temperature of 70 degrees C or higher is going to favour elimination. Substitution takes place in aqueous conditions, whereas for elimination to take place, there needs to be no water present. Both reactions require the halogenoalkane to be dissolved in ethanol, and both of them are going to require the presence of some hydroxide ions, so either potassium or sodium hydroxide. The other thing is that whereas primary halogenoalkanes are more likely to undergo substitution, secondary halogenoalkanes are more likely to undergo elimination. So in this elimination mechanism, we're going to have some hydroxide ions, which have come from either potassium hydroxide or sodium hydroxide. And it's important that you understand that in this reaction, the hydroxide ion is acting as a base, not as a nucleophile. This mechanism is a little bit more complicated than the nucleophilic substitution was, but bear with me, we're going to get this. Our first step is to identify which carbon is bonded to the halogen. So here is this carbon on the right-hand side. Now from there, I'm going to go to the adjacent carbon. So I'm not actually interested in the carbon that's bonded to the halogen, I'm interested in the one that's next to it. So you can see here I've put a little yellow bubble around the one on the left-hand side. Then I'm going to find a hydrogen that is bonded to that carbon. So any of these three here will do. We're now ready for some curly arrows. So remember, our hydroxide ion is functioning as a base, which is a proton acceptor or a hydrogen ion acceptor. And it could attack any of these three hydrogens with orange circles around them on the left-hand side. So my first curly arrow is going to go from the lone pair on the hydroxide ion to one of those. So in this instance, I've picked the bottom one just because it's the easiest one to keep my page straight. So that hydrogen is going to move away with this hydroxide ion, forming a water molecule, which is one of our products. And so that hydrogen doesn't need the electrons that are in its bond with its carbon anymore. So both of those electrons are going to be given back to the carbon. So my left-hand carbon now has one extra electron, and also it's missing a bond. So the next thing that's going to happen is that my bromine on the right-hand side is going to withdraw the electron density in that covalent bond back to itself. And that's going to allow it to leave as a bromide ion leaving group. So now I have my left-hand carbon has an extra electron and is missing a bond, and my right-hand carbon is missing an electron and a bond. And so the way to sort of square this is that the two of them form this double bond between them, and that's how we end up with our alkene. While primary halogenoalkanes only have one potential product in this situation, secondary halogenoalkanes have two different products that could be formed. So let's follow our starting process again for finding which hydrogen is going to be attacked. We start by looking for the carbon that is bonded to a halogen, which is my second carbon here, you can see is bonded to bromine. And from there I need to move to an adjacent carbon, but I've got two options. Either I could move to this first terminal carbon, or I could move to the third carbon. Then I'm going to be thinking about the hydrogens that are surrounding them. So either these three on the right, or the two up and down on the third carbon, and any of those could be attacked. And depending on which one is attacked, we're going to get different products. What we can say for certain is that we're going to have a bromide ion leaving group and also a water molecule made from the hydrogen that is eliminated and also the hydroxide ion. But as for the other product, we've actually got two options. So option one is that this terminal carbon has its hydrogens attacked. So any of those three, we would get the same product. So I get my first curly arrow going from the lone pair of the hydroxide ion and attacking one of those hydrogens. Then the electrons in the bond between that hydrogen and the carbon go back to the carbon. And then we're going to lose our bromide ion as our leaving group. And that's going to give us a product that looks something like this. Alternatively, rather than attacking the hydrogens that are bonded to the terminal carbon, instead our hydroxide ion might attack either one of the hydrogens bonded to this third carbon. So my lone pair is attracted to the hydrogen. The electrons in the bond between the hydrogen and the carbon go back to carbon. The electrons in the bond between the carbon and the bromine go to the bromine, leaving us with our bromide ion leaving group. And what we're left with is butene. Now, if I draw this out in a slightly better format, you can see that what we've got here is our Z isomer. Z for zusammen, the German word for together, because the two atoms that have the highest atomic number are both on the same side of that double bond, which is unable to rotate. However, if instead we attack our upper hydrogen, then we end up with a hydrogen in a slightly different place, and therefore we end up with our E isomer. The story of ozone depletion is very much tied up with a class of molecules called chlorofluorocarbons, also known as CFCs. These are basically alkanes where all of the hydrogens have been replaced with either fluorine or chlorine. Under normal conditions, they're very unreactive and they're also non-toxic. Thomas Midgley, who introduced them, famously demonstrated how safe they were by breathing in a lungful and then blowing out a lit candle. For a long time, the short-chain CFCs were used as propellants in aerosol cans, blowing agents in foams, and as refrigerants, while longer-chain CFCs were used for dry cleaning and in degreasing solvents. The problem is that in the stratosphere, these CFCs stop being stable, and they speed up the breakdown of ozone. Nowadays, we've replaced them with second-generation replacements like hydrofluorocarbons instead, because these do not attack ozone. You've probably heard of ozone and the ozone layer for years, but chemically, what is it? Well, regular molecular oxygen is O2, but ozone is O3. It's formed from an oxygen molecule that has bonded together with an oxygen radical, so we've got 3 oxygens in there. Ozone forms a layer in the stratosphere that protects us from harmful UV radiation. However, it can be attacked by chlorine radicals, which are produced from CFCs by photolysis, also known as photodissociation. Photolysis, or photodissociation, happens when certain bonds are exposed to UV light, causing them to break. The key thing about the photolysis of CFCs is that the bonds break homolytically. This means that rather than one atom taking both of the electrons in a covalent bond, as we've seen in our nucleophilic substitution and elimination mechanisms, each atom takes 1 electron. This makes them incredibly reactive. We show that these are radicals with an unpaired electron by drawing this little dot. When ozone reacts with chlorine, we call this mechanism free radical substitution, and there are 3 steps to the process. The first step and the last step are only going to happen once, but in the middle, this propagation step can happen over and over and over again, breaking down loads of ozone molecules. Our first step is called initiation, and this is when UV light causes a carbon-chlorine bond to break homolytically to form 2 free radicals. You could get a little 1-mark question that asks you what the symbol represents. So we know that it means it's a free radical, but why is it a free radical? What does it have? Well, that little dot represents an unpaired electron. So our chlorine free radical is then going to go on to do these propagation steps. So it's going to start off and it's going to attack an ozone molecule, producing a chlorine monoxide free radical and also an oxygen molecule. That chlorine monoxide free radical is then going to go on and also attack ozone. And that's going to produce 2 further molecules of oxygen and get us back our chlorine free radical. Now, there is another option where that chlorine monoxide free radical joins up with an oxygen free radical to produce an oxygen molecule and a chlorine free radical. But to be honest, that one is not mentioned in the AQA spec, so I wouldn't worry about it too much if you're taking the AQA exams. Whichever path we take, our chlorine free radical can just go back round to the start of the propagation step and attack another ozone molecule. And so we can just go round and round this second step over and over. Eventually, however, we're going to get to termination. So the easiest way for termination to happen is if one chlorine free radical meets up with another chlorine free radical and they bond together to make a chlorine molecule. However, it's also possible for our chlorine monoxide free radicals to get involved, either with 2 of them or with 1 of them and a chlorine free radical. In that case, we would either make chlorine peroxide or dichlorine monoxide. Thank you very much for watching, and I hope you found that a useful summary of all things to do with the halogenoalkanes. If you are finding these videos useful, then don't forget to like, subscribe, comment and share the channel, and I'll be back soon with some more A-level chemistry resources.